In 1950, power sounded like a scream.
If you stood on the tarmac behind a de Havilland Comet or a military Phantom, the noise was not just loud.
It was a physical assault. It was a phantom shriek that shattered glass, ruptured eardrums, and tore. This was the sound of brute force. It was the sound of humanity fighting the atmosphere with a sledgehammer.
But if you stand behind a modern airliner today, a massive Boeing 787 or an Airbus A350, you do not hear a scream. You feel a deep, chest-rattling thrum.
It is a low-frequency hum that carries 300 tons of aluminum and composite structure across the widest oceans on Earth.
This shift from the scream to the hum is not just a difference in acoustics. It is the defining story of modern aerospace engineering.
It is the story of how engineers stopped fighting the air and started manipulating the fundamental laws of physics to turn a fuel-guzzling.
To understand this machine and the engineering warfare occurring inside its casing, we must first look at the
Newton's second law of motion. Force equals mass times acceleration.
This equation is the rulebook. To generate thrust, which is the force required to overcome drag,
You can take a choice. You can take a very small mass of air.
The early engineers, obsessed with speed, pulled the acceleration lever. The turbojet chooses violence.
But modern engineers, obsessed with efficiency, pulled the mass lever. The turbofan chooses leverage.
Let us dissect the ancestor first to understand the flaw. The turbojet. Picture a hollow steel pipe. This is a continuous combustion cycle in its purest, most brutal form. At the front, the intake does not have a fan. It creates a shock wave to slow the air down before it enters the compressor.
Inside, a series of spinning blades, known as rotors, chop the air into smaller and smaller packets.
Behind each row of spinning rotors is a row of stationary blades called stators. The stators guide the flow. With every stage, the pressure rises. By the time the air reaches the heart of the engine, it has been squeezed by a factor of 20.
The molecules are packed so tightly that the temperature spikes violently, even before we add a drop of fuel.
Here, fuel injectors spray kerosene mist at high pressure.
Instantly, the mixture detonates. But unlike a car engine where the explosion pulses, this is a continuous, self-sustaining flame front.
The gas expands explosively, but it has nowhere to go but rearward. It rushes through a turbine, In a pure turbojet, 100% of the air that enters the intake passes through this core fire.
Every single molecule is traumatized, heated, and blasted out the back. This creates an exhaust velocity that is insanely high.
We are talking about jet gases exiting the nozzle at nearly 2,000 kilometers per hour.
This sounds impressive. It sounds powerful. But thermodynamics dictates that for a passenger plane, this design is a disaster. Here is the trap that engineers call propulsive efficiency. Efficiency depends on the relationship between how fast your jet exhaust is moving. If your exhaust is screaming out the back at 2,000 kilometers per hour, but your plane is only cruising at 800 kilometers, it leaves the engine carrying massive amounts of kinetic energy that does nothing to push the plane. It simply churns up the atmosphere, creating heat and noise.
Think of it like this. You are trying to push a heavy cart. If you stand behind it and shoot it with a high-caliber bullet, the bullet carries massive energy.
But when it hits the cart, it punches right through or bounces off. The energy transfer is chaotic. It is violent. It is wasteful.
This is what early jetliners were the sky.
The engineers hit a hard wall. To fly further and cheaper, they did not need faster exhaust. They needed to move more air. Enter the high bypass turbofan.
The visual difference is immediate. The front of the engine is no longer a small, narrow intake. It is a gaping maw, sometimes 3 meters wide. This is the fan. But do not mistake it for a simple propeller. This is a precision-engineered airfoil operating in a transonic regime.
When you look at a modern high-bypass turbofan, you are looking at a machine with a split personality. The first path is the core air. This accounts for only 10% of the total air intake.
This small fraction goes into the center, gets crushed by the compressors, ignited in the combustor, and blasted through the turbines. However, the purpose of this core is no longer just to produce thrust. Its primary job is to act as a gas generator.
It is a powerhouse designed to spin a shaft.
That shaft runs forward through the entire length of the engine to drive the second path.
This is the second path of air, the bypass air, which is the majority of the air entering the engine.
This design allows the engine to move a much larger volume of air at a lower speed, drastically improving propulsive efficiency.
The bypass air. This is the other 90% of the air.
This massive volume is accelerated by the big fan at the front, but it completely bypasses the engine core. It flows through a duct around the combustion chamber, essentially wrapping the screaming hot core in a blanket of cold, accelerated air. This is the miracle of the bypass ratio. In a modern giant like the GE9X, the bypass ratio is 10:1.
For every 1 kilogram of air that gets burned, 10 kilograms are simply pushed around the side.
By moving this massive amount of air at a slower velocity, the turbofan matches the speed of the exhaust to the speed of the plane. The propulsive efficiency skyrockets. We are no longer shooting a cart with a bullet. We are pushing it with a massive, unstoppable hydraulic ram. We are gripping the atmosphere with a pneumatic claw.
But moving that much air required a fan of immense size, introducing a mechanical nightmare that pushes material science to its absolute breaking point.
Let us analyze the fan blades at the front. When the engine is running at full takeoff power, the tips of these fan blades are spinning fast.
This creates a continuous shockwave on the leading edge of the blade. But the real enemy is not the air, it is the weight of the blade itself.
At these speeds, the centrifugal force trying to rip the blade out of the central hub is astronomical.
A single fan blade can experience a pull force of nearly 90 tons. To put that in perspective, that is the equivalent of...
The metal is screaming. It is stretching. If the material has even a microscopic impact.
The crack will propagate instantly. The blade will create a catastrophic release. It becomes a piece of shrapnel.
To survive this environment, we cannot use simple aluminum. In the past, we used wide-cored, hollow titanium blades.
But titanium is heavy. To get bigger, we had to invent something new. Today, we use carbon fiber composites. Thousands of layers of carbon cloth, stacked and cured in an autoclave. But carbon fiber has a weakness. It is brittle. It cannot handle impact. And an engine must... Imagine firing a 4-kilogram goose into a slicer spinning at supersonic speeds. The impact energy is devastating. A pure carbon blade would shatter like glass. To solve this, engineers bond a titanium sheath to the leading edge of the carbon blade. This titanium shield acts as armor. It creates a blade that is tough enough to slice through organic matter, absorb the shockwave of the impact without snapping, and
The miracle of modern engineering, allowing safe and efficient flight. But the fan is only half the problem. The real engineering torture happens deep inside the low-pressure turbine.
Remember, the big fan at the front creates thrust by grabbing a lot of air.
Because it is so big, it wants to spin relatively slowly. If it spins too fast, the tips go supersonic, creating drag and shock waves that ruin efficiency. But the turbine at the very back of the engine, the component that extracts energy from the hot gas to drive the fan, has the opposite desire. Turbines are efficient at high speeds. They want to scream at high revolutions to harvest every joule of energy from the exhaust gas. This creates a fundamental mechanical conflict. We have a fan that wants to be slow and a turbine that wants to be fast. But for 50 years, they were bolted to the same steel shaft. They were locked in a bad marriage. Engineers had to compromise. They ran the fan a little too fast, making it noisy. They ran the turbine a little too slow, making it inefficient.
This mechanical lockstep was the limit of the technology, until we decided to break the connection. The latest evolution in this war is the geared turbofan. Engineers placed a reduction gearbox between the fan and the turbine.
It sounds simple, but this is one of the most complex mechanical devices ever built. This allows the low-pressure turbine to scream at 20,000 revolutions per minute, operating at its peak thermal efficiency.
Meanwhile, the gears step down that speed to let the massive fan hum along at a leisurely, efficient pace.
Both components operate in their perfect zone.
But this gearbox is a masterpiece of stress management. It is a planetary gear system.
A central sun gear spins the planets, which walk around inside a ring gear. This mechanism must transmit 30,000 horsepower. That is enough power to drive a starting grid of 4
Slates. The friction alone generates enough heat to boil the lubricating oil in seconds. Without an advanced thermal management,
The oil must be pumped, cooled, and recycled at a rate that rivals the blood flow of a blue whale.
the result of this transition from turbojet to turbofan to geared turbofan is not just fuel savings, it is a The turbojet was a hot needle piercing the sky.
The turbofan is a volume displacement machine. By wrapping the screaming hot core exhaust in a layer of slow, cold bypass air, we shear the noise.
The cold air acts as a buffer. It mixes with the hot air, smoothing out the turbulence that creates the roar.
This is why you can have a conversation near an airport today without shouting.
So, when you see a modern airliner, do not just see a plane. See a machine that has mastered momentum. It has abandoned the brute force of high velocity for the elegant efficiency of high mass. It manages to push the atmosphere backward so we can move forward. To keep deconstructing the world's most complex systems, stay connected to Gridonix.